Okay, now we're going to talk about a different form that sugars actually exist in, and it's a cyclical form. So again, this is just to review the acetal and the hemiacetal from chapter 16. If you take an alcohol and add it to an aldehyde or even a ketone, this oxygen bonds to this carbon, and these pi electrons, or our double bond moves up, and this hydrogen transfers over there, and you get what's called a hemiacetal. So this group right here is this group, and then you form an OH. Remember, it's a hemiacetal because it's half of an acetal. Again, you have a carbon with two oxygens, that's one and that's two. One of them has an H and one of them has an OR. Remember, an acetal is just with two OR groups, just to remind you, that's an acetal. Okay? So sugars do this. I believe this was one of the exam questions for exam 2, was drawing one of these molecules in a hemiacetal. That's why I tested you on this, because I knew we were going to be using this quite a bit when we get to the sugars. So if you still had problems with that back in chapter 16, I strongly urge you to go back and review this and make sure you understand this, because we're going to be using it quite a bit in this chapter. All right, so basically what happens is this alcohol group right here cyclizes onto itself and bonds to that carbon. If you notice, it's a 1, 2, 3, 4, 5, 6-membered ring, okay, which is this, and this is what typically a sugar is. It's a especially a monosaccharide in particular, which is what this topic is about. All right, so the alcohol closes onto itself, and you get an OR group. Technically, here's my O and here's my R because that's a carbon, and an OH group. All right, so here's an example just to kind of show more of this projection. It's what's called a Hawthorne projection, where it has like a 6-membered ring like this, and this part of the ring is coming out towards you. Now, this carbon right here is what's called the anomeric carbon. It becomes the important carbon because it distinguishes between two types of structures of my sugars, either the alpha form or the beta form. All right, we're going to talk about both of these forms. The alpha is where it's going down. All right, and the beta is where the OH is going up. Now, when you cyclize, what you're using that OH that we determined the D and the L on. So it's that OH group that actually cyclizes onto itself onto the aldehyde. So this OH, the OH that determines the D and the L, is the one that closes up onto itself with the aldehyde. All right. So the first step is the cyclization, is to rotate the glucose. This is just kind of trying to show you a way to kind of figure this out. So if I were to give you a sugar and ask you to draw it in the Hawthorne projection or the cyclized projection, you'd be able to figure it out. So all they're doing is that they're just taking one and they're bringing it down. So it's like bringing this down to rotate it. And then you're going to see how this is going to close up onto itself. Okay, and then they kind of, this group 6, you kind of draw up, all right, and then you're going to eventually have that kind of add it. They don't show you, but basically this group will add in here. It depends, is it going to add from the bottom or add from the top, putting this alcohol group, once you form the alcohol, on top or bottom, and it just all depends. One is the alpha and one is the beta. All right, like I said, these are what's called Haworth. I apologize, I called them Hawthorne, but they're actually Haworth projections. Sorry about that. All right. For monosaccharides, most of them exist in the beta glucose. That's a much more stable conformation than the alpha. All right, so about 2/3 of it is kind of in the beta position where the OH is going up. All right, so this is kind of, they want you to kind of practice and draw this in the Haworth projection. So if you like this, pause the video and give it a shot. Go ahead. All right, welcome back. If you didn't do it and you want to, this is your time to stop. Otherwise, let's just continue on. So again, you put the CH2, so this group right here is this group right here. All right, and you're going to cyclize this OH onto there, and here is your compound. All right, both in the alpha and the beta. All right, the only thing that switches is these OHs. Notice you have two OHs on the top side and then an OH on the bottom. All right, The cyclical form of fructose is a little different. It's a 5-membered ring, but same thing. The oxygen from the one that determines our D and the L is going to cyclize on the ketone this time. So it's 5. 1, 2, 3, 4, 5-membered ring. So this is a little different, but it's the same, it's the same thing. You still also have alpha and beta. Notice that your CH2OH now is on the anomeric carbon. It's not next to it. So that's the difference. And I'll assign problems and you guys can practice these. All right, reduction of these groups. So notice you have an aldehyde or a ketone. You can reduce these. We've learned how to reduce them either with hydrogen and palladium. I think we also talked about sodium borohydride as a reducing agent. So these are agents that can get rid of the carbonyl and turn into an alcohol. All right, and if you do that, if you get rid of the carbonyl, all right, and just do all alcohols, this is what's called a sugar alcohol. In particular, this one's called sorbitol. All right, these are kind of sweeteners that they put in foods as an artificial sweetener. It was kind of one they used a long time ago. You might have heard of sorbitol in candies. They put them in a lot of candies. You might have heard the term sugar alcohol. They put them in diet foods. A lot of the protein bars have this in it. So that's kind of where they get these names from, a sugar alcohol. All right, and that one in particular is sorbitol, which comes from glucose. All right. The Benedict's reagent, remember we did this in one of the labs, where if you take copper and a little bit of base with an aldehyde, it will oxidize it to the carboxylic acid. It's called an oxidizing sugar. So if you have an oxidizing sugar, it goes from a bluish color because then your copper turns red, a brownish red color. Also, when we did the urine analysis lab for the diabetes, we used this reagent. Technically, it was a Benedict's reagent. It was the blue solution, and we put it in, and it turns like that brownish color. Technically, it's like a brick red color. All right, ketones, however, or ketoses cannot do that because a ketose, remember, has a ketone right here. You can't oxidize it to a carboxylic acid. So this specifically is a test for aldoses, for aldehyde sugars. All right, disaccharides, so we've talked about monosaccharides. Disaccharides are two of these linked together. Rather than having a hemiacetal, like in the mono case, all right, we have another sugar hook onto here. So this is just kind of a simple one where they have a methyl group, a methanol hooked there. But imagine if this was another sugar hooking onto there. You now have two R groups. So now we have a disaccharide. All right, and now this is where the alpha and the beta linkage is going to become important. And once you hook two sugars together, you form what's called a glycosidic linkage. Glycosidic. Anytime you see glyco, think sugar. All right, you form a glycosidic linkage. All right, and it's usually a 1,4 linkage when you have a 6 and a 6. All right, and again, you're going to have an alpha and a beta. All right, if the bond is alpha, the glycosidic bond is facing down. If it's beta, this bond is going to be straight up, and the structure is much different. Okay, names, just to kind of give you some nomenclature, 1,4 alpha glycosidic linkage. All right, the 1 carbon is the anomeric carbon. Remember, this is the anomeric carbon. Okay, on this molecule, the anomeric carbon is here. And there's the anomeric carbon there. So it's 1, 2, 3, 4. So that technically would be carbon 5. So it's a 1,4 because this is 1, 2, 3, 4. So 1,4 alpha glycosidic linkage opposed to a 1,4 beta glycosidic linkage. Notice you see how this is kind of on top of it. You kind of have a beta. These compounds are much easier to break because this is not that much of, it's more stable as a monosaccharide, but once they form, these bonds like to break pretty easily. All right. So here they talk about hydrolysis of these bonds. Okay, so hydrolysis of maltose. Okay, malt. You guys have probably heard of malt sugars. The malt is maltose. This is the structure of maltose. It's basically two glucose molecules that are bonded. Okay, so you have glucose, you have sucrose. Okay, so sucrose is glucose and fructose. Maltose or malt sugar is two glucoses hooked together by an alpha linkage. All right, and you can see You take this, you break it, and you have 2 glucose molecules. All you need is water. Okay, if you've ever had malt before, in particular in a malt, so rather than having a milkshake, you have a malt, they kind of sprinkle malt in there. It has a much sweeter taste. Sometimes people just take malt and they sprinkle it on their ice cream. I don't know if you ever had that, but I love malt and I love malts. You can even just take malt and put it in milk, malted milk. It's called malted milk, and it's pretty sweet. Sweet in the sense that it tastes sweet, but it's also pretty sweet. All right, lactose is also a disaccharide. It consists of 1 galactose and 1 glucose, and it's joined by a beta linkage. Notice this is a beta linkage, so galactose and glucose. All right, so it's a beta glycoside or glycosidic bond. Same kind of name, a different name, but the same thing. All right, disaccharides, the disaccharide bond is cleaved by an enzyme called lactase. Individuals who are lactose intolerant no longer produce the enzyme lactase. So without the enzyme, lactose can't be digested. It causes a lot of cramping, diarrhea, and a lot of gas. But you can take a supplement. If you take Lactaid or any of those pills, they are lactase. It's basically what you're doing is you are eating the enzyme lactase so that when you do drink milk or you eat ice cream or you have cheese or something that has dairy in it, your stomach has the enzyme in it. So as soon as you eat the milk, the enzyme breaks it down inside of your stomach. Even though your body doesn't produce it, you just kind of consume it. All right. Let's see. Artificial sweeteners. I definitely want to talk about this because this is a huge thing in our food industry. So here's the structure of sucrose. Notice it is a beta linkage. Sucrose breaks down very easily. Basically, the water or the saliva in our mouth is enough to actually break this glycosidic bond. All right. So sucrose is very sweet but has many calories. All right. To reduce the caloric intake but to still keep the sweetness, we've developed artificial sweeteners, which honestly is probably worse for us than just eating sugar. Aspartame or equal is one of them, and it's actually in a way, it's a diamino acid. All right, it's phenylalanine, but there's some people who can't process phenylalanine. It's not many people, but there's a condition called phenylketonuria in which you cannot break down phenylalanine. Saccharin, which is sold as sweet and low, was used during World War I. I don't know how much saccharin really is around these days. I don't really see sweet and low that often. I see equal mostly, which is aspartame, and then Splenda, of course, is kind of the newest one. If you notice, it looks just like sugar, all right, but notice you have these chlorine, covalently bonded chlorine. I will tell you, this is not good. All right, our liver has a crazy time dealing with chlorines, and when they break this down, you start forming chlorine radicals in your liver. That is not good. I mean, that is so the opposite of good. The reason why we're allowed to eat it, you might be thinking, well, if it's so bad, why does the FDA approve it? Well, it's because we can consume very, very, very small amounts of this because this is like a trillion times sweeter than sugar. So if you've ever bought the Costco-sized bag of Splenda, I don't know if you've ever seen this bag. It's like the size of a purse, and it basically weighs nothing. It is so incredibly light, but it's completely filled with Splenda. Splenda is not dense at all. It's very airy and fluffy. But if you ever hold the bag, it weighs hardly anything, and that's because you don't need a lot of it. You need a very small amount of it to have the same sweetness as sugar. All right. So let me stop right there, and when we come back, we'll start with the polysaccharide.